So this is an introduction to trees, and the way trees work, and the reason why they call them trees is because we start off with the root, right, and then we start branching out. Uh, our data structure starts branching out to different roots, and I won't necessarily say roots, but they have a parent-child relationship. So I'm sure you've seen this a lot, um, and I'm actually not really populating them correctly. We would start putting our data inside of a data structure in a tree-like manner, um, and so I'm still messing up. All right, here we go. This would be 3, and then we would have 4, 5, 6, 7, and then if we branched out more and made more nodes, uh, we would have 8, 9, 10, 11, and so forth. And so pretty much as we create new nodes or leaves to our tree, then we start expanding the tree bigger. So each node will have its own children. And so think of it like a family tree. You start off with your parents, and then your parents have kids, and then you have kids, and then your kids have kids. And so your family tree just grows bigger and bigger. And so these trees are basically built of nodes. And we're actually just going to talk about binary trees right now. And so a binary tree is pretty much a tree that has nodes, and each node can have a maximum of 2 children, right? So if we start off with one node, this is going to be our root. And then each node has a left child and a right child. And so this would be a tree of 2 levels. This would be our first level, and this would be our second level. And then if we wanted to keep growing our tree, then each of the nodes can have a left and right child. So now we would be at depth 3, and this can keep growing and growing bigger and bigger as we start adding more things to our node. So just for terminology basis, um, this would be considered a parent, right? And then the 2 here will be considered children. And when you have 2 children from the same node, they're also considered siblings, right? Because they have the same parents. Um, right? We can also consider this being a descendant, as your book would say. Uh, but you hear it called child or descendant. It's interchangeable, but they basically mean the same thing. We also have subtrees, right? So if you notice, if we look here, this right here is also a tree, right? Because it starts this, in this case, if we looked at the red circle as a tree, then this would be the root, and then these would be the children. Um, all right, and so if we get to the end of a tree and that particular node doesn't have any children, let's say we were to grow another node here, descendants here, these particular nodes here would be considered a leaf node, and that means that it's pretty much the end of that depth. That means that it didn't grow any further, and the tree pretty much stopped at that depth for that particular parent. Um, so there's a few types of trees that we can have. Well, before I do that, of course, since I added this, then that means that we have a tree, this entire tree here. And I'm just gonna use my pointer, this entire tree here that I'm circling around has a depth of 4, right? So that is the depth of my tree. But we also can consider the depth of a node. So if we think about the node that is being circled right here, this node has a depth of 2, right? That would be the depth of this particular node here. This particular node would have a depth of 2. Of course, so if we looked at this particular node as well has a depth of 2 because it has the first node and then also its children. So that's the difference between the depth of a tree and the depth of a node. So we also have, so let's talk about different types of trees. So first there is a full binary tree. And a full binary tree looks something like this. And that is basically where all levels are even. If you notice that both children of the root have the same amount of children, and they also have equal amount of children. So both the left and the right are even, right? They both contain leaves. So this is a full. We also have what would be called a complete binary, which would be something like this. So we have a complete binary. And a complete binary tree is kind of the same. It's very similar to a full binary tree. Um, uh, but but the way a complete binary tree works is that is if we have a tree here, and so let's just start off with a full binary tree that we had in our first example. All right, so this would be a full binary tree. Um, a complete a complete binary tree is basically where all the new leaves have the same depth, um, and then we make sure that we always add to the leftmost node. So so if we started adding another node here, right? We can't consider this a full binary because every node is not at the same level, right? And a complete binary says, a full binary says that this would be our tree where everything is at the same level. Every the last node has the same amount of leaves at the end. But a complete binary tree would be if we are close to a binary tree, but we have extra nodes, but the nodes are still they're still going to be as far left as possible, right? So for instance, if I were to do something like this, I couldn't consider this a complete binary tree because the nodes at the deepest are to the right and we have nothing on the left, right? If you notice here, we have nothing on the left, but we have nodes on the right. And so that is actually not a complete binary tree. To make this binary tree, we would actually want to have our nodes to the far left. And we could even, and if we were to do something like this, then we still won't consider this a complete binary tree, because in order for us to have this far left node at the bottom, we would have to have these nodes completed first. So if we had these nodes completed, then now we have a complete binary tree. So other binary trees that we have a binary taxonomy tree. And basically, binary taxonomy tree is used. You probably see this a lot. If you ever played 20 questions, most likely they're using one of these type of trees. And also, this is also a great example of why we call if else and switches branches, right? Because we start branching off. So say we want to ask a question, right? Let's say something like red or blue. Then we will make two choices here, and one would be for red and one would be for blue. And then after that, we can say, is it liquid? Right? Maybe we can ask if it's liquid on both sides. And, then we can have a yes or no. And maybe once we do that, if they say yes, then we can say, all right, then it's blood. If they say no, then we can start asking other questions, right? Another question, so we can try to figure out what we're looking for. We can say, is it blue and it's liquid? We can say, okay, then is it the ocean? Or is it, what else is some blue liquid? I can't even think of that. Ink. If we say yes or no, then we can start branching off, and we can use these different leaves of the tree to narrow down whatever we're looking for. And this is actually a really good way to do when we want to do big O of log n, because we are able to eliminate and not have to search the entire data structure to find what we're looking for, because we can base it off of the knowledge that we received from the previous node. If I'm at liquid and it's and they say no, there's no need for me to start looking to the left side, because it has already been determined that it's not a liquid. So anything further down here is not going to be helpful for me, because I already know I need to start traversing down this path. And so that's basically what a taxonomy tree is. All right, so let's get into some implementations of a tree. And so one of the easiest ways to implement a tree is to have an array hold your data. And of course, we know the pros and cons of an array. But what's really good about an array is that it does give us random access. So we can actually traverse through our tree very quickly, because an array does give us random access. And so basically, the way an array works is, let's say we created our array and we felt that our tree would have no more than 100 nodes. So I set my root to be at index 0. And now if I want to add a child to my node, if I want to add a child to my root, then basically, let's say I'm at 0 and I want to add a child, then of course I would probably want to put my let child at 1, and my right child at 2. And when I say 1 or 2, I'm referring to indexes. And so that would be easy, right? But what happens when we start going here? And I want to put my left child at 3, right? Of course. And then I put my right child at 4. Now that can get really difficult, right? If we're trying to use random access, this wouldn't work um, if we didn't have some type of formula, right? Because if I am trying to put in something to my parent child, excuse me, my parent, and I know my parent is 1, then how do I determine what the indexes are for the children? Um, and luckily with an array, it's really easy to do that. We can just use a formula, and basically the formula goes like this: our left child is always going to be 2 times the parent index plus 1, and the right child will always be 2 times the parent index plus 2, right? And so knowing that, I could say, hey, put something at parent 100, and I will automatically know that the children would go at 201 and 202, just because of this formula. That means I don't have to traverse and find the node at 100 and then attach the left and right node to it. I already know that if my parent is at index 100 inside of my tree, then the left child will be at 201 and the right child will be at 202. And so that's one benefit of using an array in your implementation. Of course, the drawbacks are that you have to have an idea of how big that tree is. So you're limited. If you need to add more than 100 nodes to your tree, then an array implementation may not be useful. It can be useful if you know that it's 100, but if you're not sure if it's going to be 100 or more, then an array implementation is not going to be good, because you can run out of space, and then you're pretty much your tree cannot be used anymore. Of course, using a dynamic array, we can fix that. But of course, there's always the maintenance as well. If your dynamic array runs out of space, of course you can reallocate more space, but that does require you moving your nodes over to the new dynamic array, and it also requires you having to keep track of size and amount of items in the array, and that actually applies for array implementation too. So of course, you know where we're leading to, which would be a linked list implementation. And with our linked list implementation, it's going to be a lot like, and I shouldn't call it a linked list implementation, but I'm going to. But of course, when we do it that way, a better word would be a node implementation, right? And when I say node, I'm not talking about the node from a tree, but I'm talking about our good old-fashioned class node that we are used to now in our linked list. And so instead of our node having a next and a previous, or however you implemented your linked list, we will pretty much implement our node so that it actually has data. And let's say we template it, so we can say T data, which is very similar to our old node. But this time we're going to have 2 node pointers. And I wrote that wrong. These are being T's. And of course, you have to put your template class here. I think I can say that without really having to say that, but I will just put it here just to make sure we're on the same page. So I have my node pointer, and this is going to be my left child. And then I have my node pointer, which would be my right child. Right, and we should know now that this particular node will point to the next node in the tree that also has its left and right child if needed for that tree. Right, so I don't think we need to go too in depth on how we would connect these nodes. We would do it the exact same way that we do our linked list. We basically just dynamically allocate a new node and connect that to the left child, and then connect one to the right child, and then as we add nodes, we will start pointing the left child of the new node to the node that we are going to dynamically create. If you don't understand what I mean by that, please go back and review chapter, I believe that's chapter 13, or chapter 9, chapter 8. You can figure out what chapter it is. Go back and review the linked list chapter. By now, all of us should know how to write a linked list and create a linked list. So basically, the implementation is going to be very similar, except for now we're using a node that has 2 pointers to point to our left and right child. In our book, there was one thing in our book that I'm assuming a lot of people will find confusing, because the book refers to returning nodes to the top of the heap, and they actually never mention the word heap anywhere else in this chapter. And so a lot of you are probably wondering what the heck is a heap. And basically what it's saying, to the top of the heap, right? If we have a tree that looks like this, right? The top of the heap is pretty much here. If we're saying return to the top of the heap, that means that we're gonna go pretty much go back to the beginning of our tree. And they mentioned that in a function called tree clear. And the tree clear is basically a way for us to get rid of all the nodes in our tree, because remember, these are dynamically allocated variables, which means that we have to delete them from the memory, otherwise we're going to get a memory leak, right? And this is a really terrible tree that I'm drawing. Let me try again. Let me make this a little bit bigger. All right, so we have our tree here. Let's start off a little bit bigger. We have another node here. We have another node here. And I'm gonna try to make this, I'm gonna give this a depth of 4. And I'm gonna try to illustrate how this clear tree algorithm is working. All right, and so before I do that, I just want to talk about what depth first is and what breadth first is. So if we were traversing through our list, and let's say our list looks like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if this is our tree, and I was going to traverse through my tree at breadth first. If it was breadth first, that means that I'm going to go to my root node, I'm going to get the value, and then I'm going to go to each of the children starting at left, right? So I'm at 1, and then I'm going to go to the left, which is 2, and then I'm going to go to the node's right child, and I'm going to print that one. And then I'm going to go to my left node's left node, and I'm going to print that value, and then I'm going to go to the right, and then I'm going to move over to the next node, which would be at 3. Which would be at 6. I'm going to do 6, and then I'm going to go here to 7, right, and so forth and so on. And if you can see, we're just pretty much going in order. I'm going to take care of each of the children of each node as I go. Depth first is a little bit different, right? So let's say we start at root node. I'm gonna do depth first. So I'm gonna type in my root node, which is 1. Then I'm gonna go to my left, and I'm going to print out 2, and then I'm gonna go to its further left, and I'm gonna print out 4, and then I'm gonna go all the way down to 8, all the way down till I hit a leaf node. And now I hit my leaf node, and so now I'm gonna go to back to 2, and I'm gonna type in 5, and then I'm gonna do the left. Oh, sorry, I actually did that wrong. Actually, now that I reached 4, then I'm gonna type in 9. And then I'm going to go back to 2 because I took care of my left side now, right? If you notice here, I took care of the left side. Took care of the left side here. And then I started taking care of the right side. Now I'm gonna go back and take care of the left side here, and then take care of the right side. So basically I am going to say we ended at 9, so now I'm going to take care of the right side of 2. So then I will put in the number 5, then the number 10. So I completed the left side here. Now I'm going to go to the right side, which is basically going to give me 11. And now I completed the very left side of my root node. Now it's time to go to the right side. And again, we do breadth first. So now we're gonna do 3, and we're gonna keep going to the left. The left will be 6. We keep going to the left, it's gonna be 12. We satisfied our left side. So now I'm gonna continue to the right to finish the left side. And so all I have left is 13. So I write in 13. Now it's time to complete the right side of node 3. So the next number would be 7, and then it would be 14. All right, and so the left side of 7 has been completed. Now I'm gonna finish the right side, which would give me 15. And now I've did a depth breadth excuse me, a depth first search. So you notice when I did a breadth first search, my numbers pretty much came in order. But that will change when you do a depth first, because we're gonna do all the left side first. We're gonna go all the way down till we get to the end of, until we hit a leaf node, right? So that means when we get to the end of the tree, and then we're gonna continue on until we have printed out the whole tree. So the reason why I even went through all of that is because when we do a copy tree, when we do a clear tree, we want to make sure that we don't start cutting our tree off in a place where we're not able to delete the remaining of our nodes. Right? If I was to go and try to delete this node first, then I will no longer have access to these nodes here, and therefore they're going to be leaked in memory. So when we do a recursive call, we want to make sure we go to the depth of our tree and then start deleting those nodes. So we will traverse all the way to our leaf node, and then we will delete this node. Right? Now we are back here, and then we want to go and we want to delete this node. Now we're here, we can delete this node. Now it's time to go to our right. Right? So then we go to our right, we're going to traverse all the way to the end of our tree on the left side. We're going to delete that node. And now we're back to the parent. And since the left was deleted, now we can delete the right. And now we can delete this parent. And that leaves us with our node. And so now we can delete our root node, and then we can set our root equal to null pointer. And now we successfully deleted our tree without having to without a memory leak, right? So if you look inside the book, it gives you a recursive function, right? And the recursive function is pretty much setting it's going to say it's creating a binary. Well, it pretty much is creating a node. So I'm just going to say node for short. So we're creating a node pointer, and it's called child, pretty much. And we set the child equal to our left node, right? In this case, it said root pointer node. And here it had a function called left, right? And then it's going to call that function again. So before it actually does any deletion, it's going to call the tree clear function again, right? Which is a recursive call. And then we're going to pass in that left node that we received from the previous line of code, right? So let me just write the function name here. This is tree clear, and it's going to take in a node. And please understand that this is pseudocode, so definitely make sure you write this code properly. I just want to kind of give you an illustration of what's happening. So I pass in the root, and then each time around, I'm going to get the left child, right? Before I do anything, I'd make a recursive call. So that means I have my tree here. All right, and so if I'm passing in the root, the first thing it says is to get the left child, which means that it's going to pass in this node now. But before it does anything else, it calls itself again and says get the left node. So now it's going to get this node, and it's going to do that until it finds a leaf node, right? Once it finds the leaf, once it is at the leaf node, then it's going to do the same thing. It's going to pass in the right, so now it's going to pass in this right node. And then it's going to start deleting those nodes. And that's how we're able to actually do this recursively. We want to get all the way to the bottom of the node. So we use our recursive call to get to the leftmost. Then we call clear on the rightmost. Then after we do that, we start deleting the actual parameter that was passed to the function. So let me just finish writing that out. So after we do that, we're going to say child is equal to root pointer right. So we traverse all the way to the left, then we're going to traverse all the way to the right, and then we're going to start deleting. So we'll say delete root pointer, and then once the root pointer has been deleted, we just set that equal to the null pointer, and we successfully deleted our our tree. All right, and our secret word is book, and we're gonna continue on with copying the tree in just a moment.